Hi, I'm Dr. Incognito. In this video, we're going to discuss the span of vectors. So let's suppose that V is a vector space, and we're going to define the span of the vectors V1, V2, V3, etc. up to Vn, where all of these vectors are elements of the vector space V. So the definition of the span, it is the set of all linear combinations of the vectors V1 up to Vn. So in other words, the span of V1 up to Vn is the set of all vectors of the form AV1 plus, we say A1V1 plus A2V2 up to ANVN, where the coefficients A1, A2 up to AN are real numbers, working with a real vector space V. So A1, A2 up to AN, these are real numbers. So the span of the vectors is the set of all possible linear combinations of the vectors. This is the set of all, in words, linear combinations of the vectors V1 up to Vn. Let's look at an example. Let's take a look at what this means in, say, R2. And let's begin with just one vector. First, we'll begin with the span of the zero vector. The span of the zero vector. The definition is that it would be the set of all vectors of the form A times the zero vector, where A is any real number. But of course, A times the zero vector for any scalar A is the zero vector, which in R2 is 0, 0. So the span of the zero vector is simply the zero vector itself. Just that one, if that's the zero vector, then the span of the zero vector is just that very same dot. Now let's suppose we have a vector in R2 which is not the zero vector. So it's got at least one non-zero component. Then what does the span of V look like? This would be the set of all, when making a linear combination that only has one vector, there's not going to be any pluses, it's just the multiples of that one vector. It's the set of all AV such that A is a real number. And geometrically, let's say there's the origin, there's the vector V. So things like 2V and 3V and negative V and negative 2V, those are in the span of V. So if that's V, then 2V would be something like that, and 3V would be something like that. Negative V would be thereabouts. And now to help simplify the picture a little bit, let's say that there's 0, and let's just put dots at the terminal points. So let's say V would be here. So that dot will correspond to V. Instead of drawing the whole arrow, this dot will be at 2V, this dot will be at 3V, this dot will be at negative V. So here we've just chosen some select coefficients. This is 0V, if you wanted to think of the origin as being a multiple of V, it's 0V. So negative 1V, 0V, V, 2V, 3V. And what's going to happen if we let this coefficient vary? I've just picked a few special values with the coefficient. But what's going to happen is half V is going to be there, 4V, pi V will be somewhere in there, the square root of 2 times V will be there, negative 3/4 of v would be there. And as we let the coefficient run through all the possible values of r, we will get every possible dot along this line. So we think of the span of a single vector in R2 or R3 or R4, for that matter, to be a line. It goes through the origin. That's very important. Our line goes through 0, 0. In 3 dimensions, it still goes through the origin 0, 0, 0. Now let's have a look at 2 vectors in R2. Suppose we take the vector u to be like that, and suppose we take the vector v to be like that, where let's suppose that these 2 vectors are collinear. Let's suppose that they're collinear. Then geometrically, suppose that these 2 vectors are collinear, then the span of uv, which in symbols would be the set of all au plus bv, such that a and b are real numbers. Since it seems here that v is about a half u, v is a multiple, I'll say a half, v is a multiple of u, so that means that au plus bv is really just the same as au plus b times a half u. And that means that au plus bv is really just a multiple. It's a plus b over 2. A and b are real numbers, so that's a real number, times the vector u, which is in the span of u, which is, as we discussed in the last example, that would be a line. So if these 2 vectors line up, then the span of the 2 vectors is just a line. So the span of these 2 vectors is a line, since u and v are parallel. U is parallel to v. They're parallel vectors. So if you have parallel vectors like this, then the span of the 2 of them is just the span of either one of them. So to make things more interesting, let's take 2 vectors u and v which are not parallel to one another. So if we have u and v, 2 vectors in R2, say, which are not parallel, something like this, here's u and here's v, then this is significant. The span of the 2 vectors is going to be a plane. Since I'm working in R2, I'll call it all of R2, but more generally, if u and v were vectors in R3, then the span of 2 vectors would be a plane. A plane in R2 must be R2 itself. So in general, the span of 2 vectors in some n-dimensional space, Rn, is a plane in Rn. To see that, here's u, here's v. Given any arbitrary point in the plane, here's the origin. Given any arbitrary point in the plane, you could access that point using u and v. In other words, you could think of that point, let's call it, there's our point right there. And so we'll think of that as the point as really being a vector. Let's say it's w. Then we could express w as a linear combination of u and v. In other words, we could write w as au plus bv for some coefficients a and b. And so w will be in the span of u and v. And it doesn't matter where you put w in the plane, I'm going to put it here. So to see this, let's extend out the vector u a little bit. extend out the vector v a little bit, and then make a parallelogram with sides parallel to u and v, and using the origin and the terminal point of w as a diagonal. So here, parallel line there. I didn't do so well earlier with parallel. Let's see how it goes here. That's not so good either. And parallel here. So that's supposed to be a parallelogram. I think this one's a little off. Let's try that one again. That's a little better. So there's our parallelogram. So what you have here is that this green vector here, this one is some multiple of u. This one will be a times u. And this red vector here is a multiple of v. We'll call that b times v. Then w is clearly au, the green one plus the red one, au plus bv, which is in the span of the two vectors. So the span of two vectors will either be a plane or a line. It depends on whether the vectors themselves are parallel. And this is important. This brings up the whole concept of linear independence. These two vectors are considered linearly independent, the term coming from they lie on the same line. So they are linearly dependent. And their span is just that same line, that common line that they lie on. Whereas these two vectors are linearly independent. They lie on different lines. And so their span will make a plane.